All right, everyone. How are we doing today? Doing okay? All right. Anyway, uh, for the benefit of those of you who are watching the recording of this, we were dealing with some technical issues, and so the video is going to be a little bit short. That's because we're starting in the neighborhood of 15 minutes late due to shenanigans. My HDMI cables decided they weren't going to notice that they were plugged in until after they had been unplugged and plugged back in several times. Including an embarrassing phone call to the tech people who asked me to do that. And of course, when they asked me to do it, it worked. So, all right. So let's get started here. There are two things that we need to accomplish today. Fortunately, uh, today's material isn't going to be something that the lost time is going to hurt us on a ton, because most of the examples that we need to deal with today are mostly visual. Okay. So we're going to get by with some sketches, and then also, time permitting, do a couple of computer pictures for everyone to look at. But what I was going to recommend, regardless of how today went, was that you take a look at what's going on in the textbook for these, and then producing the online notes for these sections is a big task because there's a bunch of pictures to be made. So I'm still trying to get all of that sorted out for one of the sections, which is why those links haven't been updated yet. So anyway, today I'll try to give you the impression of the main ideas of what things to be looking for, and noting that in particular for today's section 14.2, in which we're going to be talking about limits and continuity, will address some issues regarding to that, and make sure that we make note of the special way that we have to think about doing the computations for that. Okay, and then someone had a question in the back. This is the tail end of 14.1, and then after we talk about this, then we'll transition into 14.2. Okay, yeah. All right. So I was rambling for long enough that I happened to answer their question. All right. Okay. So to get things started, and again, this is the end of 14.1. If we have some surface, and again, it's kind of hard for me to draw these in a way that is maybe super illustrative, okay, without using the computer or something like that. But we have some kind of surface that is suspended above our domain here. And if I choose some height, say z equals 2, and then use a plane to slice through the surface, what's going to happen is there's going to be some curve that is generated as a result of me slicing through the surface at that point. Okay? What this is going to do is make some curve. It looks like this. All right? And this is what we call a level curve. Okay? Or a level set, if we think about it in terms of the collection of points. The idea being that when we make this cut, we look at the intersection between the cutting plane and our surface that we started with. And if we use several of these cutting planes in order to get level sets for many different values of z, then we can come up with potentially a two-dimensional representation of the surface. Okay, something that gives us an impression of what is going on. so get down here. Again, several different representations for this function here. This is going to take a second to load. But here is the kind of thing I'm talking about. Okay, we have some kind of surface, all right, and then for each fixed height, what we can imagine is some kind of horizontal cutting plane. Okay, well, horizontal planes are when we set z equal to a constant, and then for each of these planes, we can go through and draw the curve that represents the intersection between the surface and the plane. And for more complicated figures, okay, we can use these pieces of information in order to help us extract information about from the curve, okay, or from the surface, excuse me. So these sequences allow us to, in a situation where we maybe don't have access to powerful 3D computer-based drawings, still represent some complicated things. Now, this shows up in a situation that you may have seen this, and this is examples of these are shown in the textbook as well. They're quite good, but you can either think of these as being named a contour map or a topographical map. All right, and so if you were doing some kind of navigation, all right, by walking around, okay, maybe you're a park ranger, or maybe you're involved in the military or something and you're scouting a region, okay, what you would have is this kind of map available to you, all right, if you don't happen to have high-tech GPS gear that you want to run around with, or maybe you're trying to be sneaky and don't want to send electronic signals, you would do it the old-fashioned way. But each line on this map represents a particular elevation. You'll see that at several points these elevations are marked. Okay, and so if you were to travel along one of these paths, your altitude will remain the same. Okay, but if you try to traverse a region and go from one of these lines to another one, you're either increasing or decreasing in your elevation. Okay, and the spacing in between these lines, because one of the conceits for these maps, unless otherwise marked, is that every line represents the same kind of spacing, especially if you're doing these kind of topographical maps. So from here, we see that there's a designation of 600, and here 650. And so moving from 600 to 650 is obviously uphill, okay? And the closeness of these lines tell you how steep the grade is of that region, okay? So if you want an easy path, you stick to where these lines are farther apart because you're not going uphill or downhill, okay? But if you want to change elevation quickly, then you would go that way. All right, and then here's another kind of example of this that puts the two things side by side, so we can see what the contour version looks like, and then also the three-dimensional version. Okay. So I'll get the table of contents updated with the addition of 14.1 later on today. I still have about half of 14.2 to make the examples for. But so we'll get that going. Okay. And then before we move on to 14.2, does anybody have any questions about this? Seems okay. All right. It's mostly looking at the pictures and understanding the idea, and then knowing that this is another thing that needs to be incorporated into our repertoire of being able to understand three-dimensional objects represented in kind of a limited way, because we're brushing up against that 3 dimensions is all we've got, visually and conceptually. It sure would be nice if our brains could handle 4 or 5 spatial dimensions, but that's not quite how it works. Another thing that I want to mention before we start this next section, just kind of so it's out there, has anyone heard of something called flatland? Well, I'm referring to specifically a thing. There's a series of videos or series of ideas where to kind of push everyone into being able to conceptualize what maybe 4 or 5 dimensions looks like as someone who is bound to 3 spatial dimensions. There is a reduced dimension world called flatland, all right? And the conceit of it is that you see what we know what 3D world looks like, right? But you get to see what happens in 3D if you can only maybe see 2 dimensions. All right, and how does that work? Okay, because they live in flatland, right? But stuff happens in 3 dimensions, and they only see their 2 dimensions of it. Okay, and it would be a way to incorporate the ideas of we can only see 3 dimensions. So what does 4 or 5 dimensional stuff look like to us if we only have a partial indication of what's going on? To like YouTube videos and stuff. Okay, and someone in the chat also knows, at least has heard of this. Okay. All right. So let's now talk about limits and continuity. All right. We have introduced a new type of thing, which of course is a function that has several independent variables and maps potentially onto several dependent variables. Okay. Now, for the purposes of our introductory sections on this, we're keeping the examples as simple as possible for now, which is mapping 2 independent variables onto a single dependent variable. And so this, of course, is our idea that z is equal to f of xy. Okay, but in theory, what I'm about to say applies to having multiple dimensions here. Okay. And so we say for every epsilon greater than 0, we say that the limit as x approaches a of f of x equals L if there is a delta greater than 0 such that if the distance between x and a is less than delta, find the distance between f of x and our proposed limit is less than epsilon. Okay, so the way that this works is that we specify an error bound. We say that we have to be at least this close. Okay, then this limit exists if there is a corresponding input precision to this epsilon. So delta in general is a function of epsilon, such that if x is close enough to the point to where I'm trying to evaluate the limit, less than delta, then that forces the value of the function, the distance between the value of the function and the limit, to be less than epsilon. All right, sorry, I need to take a sip of my drink. Okay, so does this make sense? Yes. All right. I was just asked if it is important that it makes sense. It's like, why in the world would I spend lecture time talking about it if it didn't matter? Okay. All right. Like, I may not expect you to often be able to prove that limits exist in this context, but you need to understand the idea. Okay, so let me draw a sketch. Now, before we move on, there's one small thing that I want to point out about this. Your book defines limits like 4 times, 4 different ways, all using this basic structure and then adding bits and pieces each time. I think that's a waste of time. All right. In this section, they just talk about limits where you have 2 independent variables and 1 dependent variable. Okay. We know about vector functions. There's no reason for us to not just think about it in terms of vectors now. Right? Okay. We know what the distance function looks like for Rn, right? It's just the square root of the sums of the component squared. And if I need the distance between 2 things, I just subtract each of the things component-wise and square those. Okay, so when we're talking about that, that's what we mean. We want the distance between the vectors to be small. Okay, but since for this example that I'm about to draw, I have a 1-dimensional output for my function. That's how I'm going to draw it. But in order to get the definition to be as general as possible, you just underline L, right? And maybe technically underline F because it would be a vector valued output for the function, right? In the textbook, F would be bold-faced, right? So, but here's the idea. We have our coordinates. And we have some surface that lies above the coordinate plane here, right? There's some point down here where I want to find the limit at. And what I do is I specify some disk around that point. all of the points that are up to delta away from A, right? And so since we're in 2 dimensions, it's a disk. If we were in 3 dimensions, it would be a sphere. And if we're in more than 3 dimensions, it would be a hypersphere, which is what we call spheres that have more than four more dimensions. Okay? Now, this corresponds to some stuff going on here, right? There's a version of that circle that shows up on the surface. Okay? Imagine I have a cylinder, okay? Like a cookie cutter. And that cookie cutter comes down and it slices through the surface. Okay? So that's what that pink line is there. It's where that cylinder slices through. Okay, not exactly like a cutting plane like we talked about for the contour stuff. It's projecting that circle onto the surface. Okay. Thank you. All right. The cookie cutter thing is quite popular here in the classroom. All right. Okay. So what we have is there's going to be some minimum height on this, and there's going to be some maximum height on this, right? The way that this shape is cut into our surface here. And of course, what we want to know is what's going on with the limit L here on the side, right? And what should happen is as epsilon shrinks, everything should be squeezed down to a single point, right? This down here will get smaller, okay? And the projection of that onto the surface will also shrink. Now, we've also all taken calculus, and we know that the actual function doesn't need to be defined at that point, right? It just has to appear that there is a single point that we're getting pushed to as that ring diminishes. Okay? But it could very well be the case that the value of the actual function is some other weird point floating around in space because it's math and I'm allowed to do that, right? Or there could be a hole in the surface at exactly that point. And that's okay too, right? In both of those cases, the limit exists. What we can't have happen is weird stuff like, how would I even draw that? I'm not an artist. So imagine you had like a fold in the surface or something, right? To where if I were trying to come at the limit this way, I would get this answer down here. But if I came up on the top part, it would give me some other value. Okay? That's a problem. So we need to make sure that we're a little bit more careful about how these things go. Okay? Let me plot an example of this quickly here. And then it's Come on, internet. All right. Oh. Okay. So we need to zoom in here. We're gonna have to zoom away, and it's gonna take a little while. Okay. So this is the kind of situation with a ridge that I was trying to sketch. Okay, and you can see what's going on as this gets filled in. So here's the surface, all right? And you have something that maybe looks like something you would have folded up to like get people to point at stuff and answer questions when some of us here in the United States were younger. But this angle, I think, shows off the folds pretty well. Okay, at the top region, you have a crest that you can follow along with here. All right, and we're interested in what the limit of this surface would be as we got close to the origin. Okay, so we're looking at what happens as we get close to this point here. And if I come along and come on some path like y equals x or something like that, okay, we see that I'm going to be traveling up here on this top ridge, and as far as I can tell, I would come up here and collide with the surface up near whatever this value is, right? Okay. But if I were to come along this line down here, okay, I can get all the way to the origin, except I think that I'm down here and at some negative value. Okay? And because these two limits fail to agree, the limit does not exist. Okay? We have two different directions that we're coming in that don't give me the same limit. Okay? Now, we know that this kind of thing can happen from our understanding of one-dimensional limits, because for 1D limits, if I had a limit from the left and I had a limit from the right, they had to agree in order for the two-sided limit to exist. Okay? For these types of limits, we have the same situation, except I don't just have two paths. I have every possible direction of approach that's possible in 2 dimensions. Okay? And it's more complicated than just coming in on straight lines. If I want to know what's going on at some point here, okay, I can come in on this straight line. I can come in on this parabola. I can come in on this squiggly line. Okay. I can take more normal looking paths too. But it doesn't matter which way I come in. All right. If the limit exists, all of these paths have to give me the same answer. Okay. No matter how complicated the path is. So this is why for these types of problems, we don't have kind of cheap computation tricks like we had for one-dimensional limits, okay? We had nice tools before like limit laws and algebraic computations and simplifications that we would do. We had L'Hopital's rule, okay? Now, in principle, those things still apply. But if we have multiple independent variables in practice, it can be more difficult to apply those properties. Okay, so we're more reliant on things like the squeeze theorem. Okay, and being a little bit more careful about our algebraic manipulations as we're working things out and using the definition of the limit, this epsilon delta business, in order to actually prove that a limit exists. Okay, so we have to do it the hard way due to multiple independent variables just kind of being a bear. Okay, but this comes with a trade-off. Okay, if we're proving that a limit doesn't exist, it's usually pretty easy. Okay, you just pick two paths that don't show the same limit, and then that shows you that the limit doesn't exist. Okay. Now, someone made a joking response to an earlier inquiry that I posed when I asked if what I was saying made sense. And part of my answer to that, and part of what I want to impress upon you all, is that these types of questions are going to be something that isn't a massive emphasis in terms of computational stuff. All right, we have other things to do, namely, like more the type of calculus that's optimization based, right? One of the things that we focus on in our study of calculus is being able to maximize and minimize things. Okay. We need limits to be able to talk about calculus. Okay. We don't have calculus without limits. All right. Limits are the fundamental idea. So we need to have a pretty strong notion of what limits are and how they exist, and under what conditions they exist, and how this would impact potentially, say, the smoothness of a function, right? Because we know that jagged things have problems when it comes to derivatives, okay? We know that things that have cusps have problems with derivatives. And if we go back and look at this picture, we see stuff that looks like cusps, right? And the ability of this, because it's a surface, to fold in on itself in weird ways, we have to understand the calculus near the origin is very, very, very poorly behaved. Okay, and that's why we care. Okay, so I know we're about out of time, and we got delayed a little bit due to the technology problems. But in closing for this week, I want to mention a couple things before we move on. Okay, number one is my very strong recommendation that you read through this section of the textbook. Okay, they have a bunch of pre-prepared, very nice visualizations for some situations where limits don't exist that you should all take a look at. And then the textbook also demonstrates a couple of cases of how one would deal with the computations for these situations. Okay, namely, it shows you how to use the squeeze theorem, which is maybe one of the tools that you would need to use for the quiz. Okay, and the other thing is what kinds of paths are reasonable guesses for limits that aren't going to work. Okay, guess easy things, guess lines, and guess like parabolas and stuff for if you want to show that a limit doesn't exist. Okay, the last bit in this section, of course, is continuity. Continuity works the way that you think it works. If the limit is equal to the value of the function, it's continuous at that point, right? Any region, because we're not just talking about intervals now, any region where a function is continuous at every point, we say that it's continuous in that region. Because we have to think about it in terms of surfaces and expanded domains. Okay? So, I made the quiz due Tuesday, I think. Okay? So if folks have questions about the quiz after taking a little bit of time and looking at it, we can talk about that on Monday. And when we come back, what we're going to be getting into is the actual calculus, okay, even though limits are definitely calculus. chapter 14 by introducing the notion of something called a partial derivative, which is the variation of derivatives that are necessary for us to be able to deal with multivariate functions. Okay, we have multiple independent variables, which means that we have multiple rates of change to consider from the perspective of doing things, and we need to make sure that we can properly handle the fact that for limits we can approach any direction that we want to, right? Okay. And if we're going to limit our scope to a small number of directions of approach for us to be able to deal with thinking about calculus, okay, we need to make sure that we firmly develop that that's an okay thing to do, right? Because I don't want to have to deal with like D squiggly line. Okay, that doesn't seem fun. All right, so we need to make sure that that's not something that we have to fight with. Okay, so that's what we'll be talking about after the weekend. Take care, everybody. Enjoy yourselves, and hopefully we won't lose time to me not having unplugged things and plugging them back in enough times. All right. Take care, everyone.